Okay, so in the previous two classes, I have gone over Newton's laws of linear motion, right? So we've covered up till parabolic trajectories. I think that covers Newton's first law, second law, and so on. And one more thing, I think the YouTube live stream, you all, I hope you know how to access it. If you don't, I'm going to put it in the chat. But you know, just for future reference, the YouTube live stream is always available on my channel on YouTube. Okay, so right, I've talked about Newton's laws of motion and laws of gravitation. I've introduced the concept of center of mass. We talked about conservation of momentum. We've talked about what is the definition of kinetic energy, how we get that definition. And we talked about, well, some other notational issues. Okay. Let's see. Okay. Sorry about that. Okay, so are there any questions about the material so far? I will post a homework set for all of this material sometime probably later this week. The homework will be on Moodle, and it will be something in a format that you can do online. Okay. All right. So now continuing with Newton's laws, there are a couple of the things that I want to cover. Let me quickly list them. So number one is harmonic motion, simple harmonic in our case. This will also include the concept of waves. We'll talk about waves. It's covered in the harmonic motion. And then the next thing is rotational motion. And again, this is a rapid review of classical mechanics. So I'll probably take this lecture and one more lecture. I think that will be it. So this will cover concepts such as angular momentum, moment of inertia, and so on. What else? I think as far as classical mechanics is concerned, this is pretty much it, right? Because I'm not going to go over things like thermodynamics and so on. Okay, so yeah, you can attend the class any way you like by Zoom or YouTube live streaming. Zoom is better, of course, but yeah, somebody has raised their hand. If you have a question, you can please ask. Okay, if you have a question. Yeah.
It was by mistake, I'm sorry.
Oh, it's okay. I mean, you don't have to be sorry for anything. Okay. All right, so now harmonic motion, which is one of the most common applications of Newton's laws. See, so as always, we have F is equal to ma, and a in the case that your mass is not time dependent. In that case, it's just ma. Otherwise, of course, you will get a dm by dt term. Okay, please keep that in mind. And the force is something that is the external force on the system. So the external force can be of many kinds, right? It can be something like this minus mgz, which is like, for instance, the force due to gravity close to the massive object, right? Close to the surface of a massive object like the Earth, for example, it looks like a constant force pointing in the downward direction, where downward is defined as pointing towards um, the center of mass of the big massive object, whatever it is, planet or moon or whatever. Then if you have things such as then, you know, I mean, if you are at a distance from the surface of the planet, okay, I don't know, sorry, I don't know. Then the force will be offered. You will have to use the full approximation, for instance, gmm by r square, the radial force. This is in general. Then other kinds of forces that you can have are, for instance, minus kx or kr, right? What is this? This is a restoring force. And this is as per Hooke's law, right? So it tells you that if you have a displacement, so I should write this as delta r. If you have a displacement delta r, then the force pulls you back in the direction of the negative of the displacement, right? And this is the kind of force that gives you harmonic motion. Then you have you can have Coulomb's force, for example. Coulomb's force again has the same form as the gravitational force. You can have a frictional force. A frictional force, for instance, looks like this. Coefficient of friction times the normal, there is a normal force between the object and the surface, right? And then the frictional force points in the direction of the negative of the direction of the motion, right? So if you want to give a directionality to it, it has to be minus v hat, where v hat is the unit velocity vector, right? So if the object is moving in the direction v hat, then the force will act in the direction minus v hat, right? Then you can also have, for instance, in the case of rotational motion, you will have a force of this kind, mv squared by r. This would be centripetal or centrifugal force, depends on the perspective that one takes. So you have these. You can add others. You can have a force due to resistance, wind resistance, for example, an object moving through a fluid, such as moving through air or through water, will experience a drag, and that drag force again looks something like, you know, again mu naught is some coefficient of which measures how strong the drag is, and then the force is, for instance, in the direction opposing the velocity, and generally it's proportional to the velocity. So I'll just write it as the vector v. So this is, for example, the drag force on an object moving in a fluid. So you have all these different kinds of forces, and for all these forces, Newton's law is the same, right? The right hand side is md 2x by dt squared. So we just have to solve it for different cases. We have solved it for one case, which is this case, right? Minus mg. We got the parabolic trajectory. So now we'll look at Hooke's law. So the Hooke's law solution gives us simple harmonic motion. Okay. So what is the typical setup for Hooke's law is that you have a spring and some mass attached to this spring, right? And we say that the spring has some spring constant K, and it has some equilibrium length, let's say L naught. Okay. So if you pull the mass such that you increase the displacement, or you push the mass such as you decrease the separation between the mass and this, and let's say there is a wall over here, then what will happen is you will have a restoring force, right? So the restoring force, so we are in one dimension only, so I don't need to use a vector sign. So the F is equal to minus K delta X, right? What is delta X? Delta X is that if I stretch the mass by some distance, so this is delta X, right? And then we normally, in such problems, we take our coordinates such that this is X is equal to 0. The equilibrium position of the mass is at 0, right? So in that case, I can just write this as minus Kx rather than delta X, because delta X is just measured from with respect to this point. So I get m d2x by dt squared is equal to minus Kx, right? This is the equation of motion, right? And now I have to find solutions of this equation of motion. Yes, Gagan.
Sir, can you please give an example of such a system in which mass is changing with time and the system is performing simple harmonic motion or harmonic motion?
In which the mass is changing with time.
Yes, as we have taken mass constant, means fixed here.
Well, Gagan, you can set up such an example on your own, no? Right?
I am thinking, but
I mean, there is no limit to one's imagination. You can set up. You can have a changing mass. You can have a rotating mass. You can have anything like that, right?
Yes.
So it's entirely like, I mean, one can come up with dozens of such examples. My goal right now is to just show how to solve an equation of this form, the very simple equation. Now, if you already know how to solve an equation like this, that's good. And maybe this lecture will be a little bit slow and not that interesting for you. But again, my goal is to take everybody along with me, and so not everybody remembers how to solve these equations. Many people have not been exposed to every topic. Okay. So if you want to come up with more complicated examples, by all means, feel free to do that. All right. And if you want, you can share that on Moodle. I have forgotten to set up the discussion forum on Moodle. I'll do that after class today. Okay? So now the thing is, how do we solve this kind of an equation? This is a differential equation, first of all, and it's an ordinary differential equation. So it's an ordinary differential equation, and or ODE for short. The other kind of differential equation are PDEs, partial differential equations. So if you have, for instance, something which involves a function of more than one variable, and something like this, this would be a PDE. This is a PDE, partial differential equation. Okay, so this is an ordinary differential equation, and also it is a linear differential equation. I put it here somewhere. This is a ordinary linear differential equation, and it's second order. So what is the meaning of these things? Ordinary means that there are no partial derivatives. Second order means that the highest derivative is the second derivative. Okay. So if you have something like the third derivative, then it's called third order and so on. Okay. Linear means that this the solutions of this equation. So what is the meaning of linearity? Okay. So this property is very important. Linearity. What does this mean? So let's say that I have two different solutions. Let's say x1 of t and x2 of t. Okay, these are both solutions of this simple harmonic motion equation of motion. SHO, simple harmonic motion equation of motion. Okay, these are both solutions. So that means if I plug in this function here, I will get equality, and if I plug in this function, I will get equality. Now I can take a linear combination of these two functions. What is a linear combination? It means I take some number alpha multiplied by x1, take some number beta multiplied by x2, right? So this gives me another function. Then I substitute this function in this equation. What will I get? I'll get m, right? Alpha x1t plus beta x2t is equal to minus k alpha x1 plus beta x2. Okay. Now this d by dt and also d by dt squared, these are linear operators, right? What does that mean? Linear operator means that if I take d by dt and I have two functions, then this is equal to the sum of the derivative of the sum is equal to the sum of the derivatives. That's what it means, right? This is the property of a linear operator. So if you apply that to this side, what you will get is m times second derivative of x1. Now alpha is just a number, so that will come out, and you will get d2 x1 by dt squared plus beta d2 x2 by dt squared minus k alpha k x1 minus beta k x2, right? Now the thing is that x1 and x2, so let me rewrite this equation slightly differently. Let me take this term over to both of these terms over to the left, then I will get this alpha times m d2 x1 by dt squared plus k x1 beta times m d2 x3 by dt squared plus k x2. Okay. Now x1 and x2 individually, they are solutions of the differential equation, right? So that means this is identically equal to 0 and this is also identically equal to 0, right? And so the sum of these two is equal to 0. So that tells me that alpha x1 plus beta x2 is also a solution, right? So this is the property of linearity. That means if you have any two or more solutions, you can take linear combinations to give you a third solution. Okay. So that is what we mean by saying that it's a linear ordinary second order differential equation. Now let us see what the solutions of this equation are. So what do we want? We want some function x. X has to be a function of time, right? Such that when I take the second derivative of the function, right? So let me rewrite this a little bit differently. minus k by m x, and k by m is some positive number, so I can write it as some omega squared x. Okay, because it's a positive number, so I can write it as the square of some number. So I want to find some function x such that when I take the second derivative of that function, I get the same function back. Okay. Now, what is an example of such function? Well, there are many examples. You can take sine, you can take cosine, you can take exponential. One second, please. Sir, I have class just now. Okay, no problem. After I get called. Okay, sir. Right. Right. So if you take the derivative of sine, what do you get? X prime t. You get cosine. If you take derivative of cosine, you get minus sine. If you take derivative of exponential, you get exponential. If you take second derivative, what do you get? You get minus sine, minus cosine, and exponential. Right? So we can take, which one of these functions should we take? We should take one, either sine or cosine, because we have a minus sign over here, right? We can also take exponential, but not the exponential of a real number. We'll have to take exponential of an imaginary number. Okay, so we'll take sine and cosine. And so we get x of t. What are the two options? Well, one possible solution is sine omega t, and the other option is cosine omega t. Okay. And these are some numbers. I don't know what these numbers are. They can be anything. But the point is that, right, this is undetermined right now. Okay. So if you take the second derivative of this function, what will you get? You will get m times the second derivative of sine omega t will give you minus omega squared, and times sine omega t, and times a. On the left side, on the right side, you will get minus k times a times sine omega t. Now this will all cancel out, and what are we left with? We are left with omega square is equal to k by m, right? So this is the definition that I used for omega in the beginning. I said that omega, I will define omega to be root k by m. Okay. Now what is this omega? Omega is the angular velocity. Okay. Why is it angular velocity? Because when you look at sine omega t, the argument of this function is an angle, right? When you take sine or cosine of something, you have to take an angle, right, as the argument. And here that angle is omega multiplied by time. So if you think of angle as some distance and t as the time, then omega is like the velocity or the speed, right? And so what will be the units of this omega? It will be radians per second. So I hope you all remember what 1 radian is. 1 radian. So we have 2 pi radians. That means if you go around the circle once, that is, you get 2 pi radians, and that's equal to 360 degrees. So that means 1 radian is equal to 360 degrees by 2 pi, which is equal to 180 by pi degrees. Okay. So how do you convert from degrees to radians? Radians, number of radians is equal to number of degrees divided by 180 by pi. Okay, this is the number of degrees per radian. All right. Now maybe all of you remember this, but in case you don't, please go back and remind yourself. Okay, so now we have these two are the solutions of my differential equation. Cosine will also have the same result. And now one thing that you can see, as I explained, this is a linear differential equation. So if I take something like this, b a plus a sine plus b cosine, this is a solution of my differential equation, a linear combination of these two equations. Okay, now you can ask, can I have other terms? Can I have some c times something else? Right, I have a times sine and b times cosine. Can I have a third term in this expression? And the answer is no. Okay, the reason for this is that this is a second order differential equation. Okay, and that means that it can only have at most two linearly independent solutions. So these two solutions are linearly independent, right? It's like when you have vector spaces. If I have a vector space, let's say a two-dimensional vector space, how many linearly independent vectors can I have? I can have at most two linearly independent vectors, right? V1 and V3. Right? If I have any third vector, V3, then V3 is going to be some combination of V1 and V2, right? So in the same way, sine and cosine are the two linearly independent solutions. Okay. Now there is another way in which you can write down the solution. As I said, you can use this exponential function. But which exponential? You have to use a complex exponential. You have to put a factor of I. Why? Because if you take the first derivative, you get I omega A exponent I omega t. If you take the second derivative, what do you get? You get another factor of I omega. So you get I omega squared. That means minus omega squared A exponent I omega t. What is this? This is equal to minus omega squared x of t. So now we get the same expression. We get the fact that the differential equation is identically satisfied. Okay. Let me see, are there any questions on YouTube? Okay, so if you happen to be attending the lecture on YouTube, please just state your name and roll number in the chat. Okay. Now again, we need two linearly independent solutions, right? So what are the two linearly independent solutions? We have exponent I omega t and exponent minus I omega t. These are the two linearly independent solutions. Okay. Now all of this, again, many of you might already know this, but if you don't, then please keep this in mind. Okay. Um, So all of this will become very important when we talk about, for example, electromagnetism and stuff. Okay. So 1 second, my apologies. All right. So how would you write it? You would write it like this: E I omega t plus b times e to the minus E I omega t. So it has the same form as this expression, right? And now you might remember that sine omega t can be written as e to the I omega t minus e to the minus I omega t by 2i, and cosine can be written as the sum of these two exponentials. So this shows you, right, that you can express this solution in terms of sines and cosines, or you can write the sine and cosine solution in terms of this solution. Okay. So this is basically the essence of rotational motion. Rotational motion or harmonic motion, they all have the same sort of equation, which is this, and the solution looks just like this. It looks like a sum of harmonic terms. That's why it's called harmonic motion, because these are harmonic functions, right? It's a perfectly sinusoidal function. It repeats periodically forever. It's called a harmonic. Okay. Now, after this, then of course one can apply this in to many different conditions. One can look at a simple pendulum, for instance. If you look at the equation of motion of a simple pendulum, yeah, please ask your question.
So the amplitude should be same in both the equations, no?
Which amplitude?
So a e to the power I omega t plus a e to the power minus I omega t to be written in the lower form.
No, they can be different. This can be A and this can be B. Why does it have to be the same?
Then we cannot write it as sin omega t is equals to e to the power I omega t minus e to the power.
No, you can write it. You will get a phase angle.
Okay. Oh, I understand. Sorry, my bad.
Yeah. Okay. Okay. So you can apply this equation to many different problems. For instance, you have the simple pendulum. In a simple pendulum, you have a downward force mg. There are two components of this downward force. One is the restoring force, and one is the force which just creates a tension along the string. So what is the restoring force? This is mg sine theta. This is the restoring force. And I can write this for small angles. I can write this as mg theta. So this is my restoring force, right? Now this is circular motion. Now what are the equations of motion for circular motion? What is Newton's law for circular motion? For circular motion, for linear motion, I have F is equal to ma. For circular motion, I have this torque is equal to, there are different ways to write it. Okay. I alpha. Right? This is one way to write it. Where I is the moment of inertia, alpha is the angular acceleration. And what is the torque? Torque can also be written as what's it? Right. Another way to write this is dl by dt, where L is equal to the angular momentum. Okay. So, and what is angular momentum? Angular momentum is equal to I omega again. Omega is the angular velocity, I is the moment of inertia. All right. Now, this is a point particle, and the length of this string is L, and the mass of this point particle is m. So what is the moment of inertia? It's equal to ml square, right? For a point particle, right, at a distance L from the center of rotation, right? Okay. And what is omega? Omega is just the rate of change of this angle with respect to time, d theta by dt. So what is the angular momentum? It is I omega, so it will be ml square d theta by dt. So what is dl by dt? dl by dt will be ml square d. So I will write this time derivative as theta dot. So this becomes theta double dot. Okay. And this is equal to the torque. Now, what is the torque? The torque is equal to the force which acts in the tangential direction times the radius, right? So the torque is equal to, this torque is also equal to R cross F. So in this case, R cross F will give me mg sine theta times L, because the cross product is already taken care of when I take the sine theta, right? And there is a negative sign, okay, because you can again convince yourself that the torque will always serve to act in a direction opposing the motion, right? So now what do you get from this expression? We take the small angle approximation and we can write this as mgl theta. So I have mg ml square theta double dot is equal to minus mgl theta. Okay. In this expression, m cancels out, one factor of L cancels out, and I'm left with theta double dot is equal to minus G by L times theta. So this expression looks exactly the same as the expression for the spring, right? What was the expression for a spring? As this guy, right? So since I have exactly the same expression, I will get exactly the same solution. So now I can write this as minus omega squared theta. Okay, like this. And the solutions will be exactly the same. Theta t, I can write it as sine omega t plus cosine omega t, or I can write it as e to the I omega t, e to the minus I omega t. In either way, either expression is correct. Okay. So this tells me that my this is a pendulum and it is executing harmonic motion. Okay. Now there are many other aspects of this, such as, for example, you can talk about the amplitude of the motion, you can talk about the velocity of motion, you can talk about the energy contained within the pendulum. All right. So all of those things I'm going to leave. You can work out all of those things once you have this solution. Okay. So I'm going to leave all of that here. Then what else did I say that I was going to talk about? Rotational motion, right? So let me talk a little bit more about rotational motion. I've already started talking about rotational motion. So what do we have? We have, this is the expression for the torque on an object. And then this is equal to dl by dt. So this is the statement of Newton's second law for rotational motion. Now there are a couple of things in rotational motion which have to do with the convention mostly. So we normally work with the right hand rule, okay? And so for all the left-handed people out there, I'm sorry, but you know, this wasn't a rule made by me, even though I'm also right-handed. And the rule is the following: that if you take your right hand, okay, and you take your fingers and you curl them like this in the direction of rotation, right? So if my thing is rotating, I put my palm in the direction of rotation, then my thumb points in the direction of my angular velocity. So for example, here I have a disk. A disk is rotating like this, okay? And so if it's rotating in like this in the plane, the direction of the angular velocity is given as perpendicular to this sense of rotation. Okay. So this is very important to understand, that angular velocity is given in a perpendicular plane, okay, to the rotational motion. And what is this L? L is I times omega, okay. Now, in general, I is not a number, okay. In general, I is a matrix. So I will write it like this with a tilde. That means it's a matrix. We assume normally we treat it as a number when you have very symmetric cases. For example, you have a ball, you have a spherical ball, or you have a cylindrical object. You know, you have an object which has some sort of symmetry. If you have a completely asymmetric object, okay, then you have to treat I as a, you have to look at the general matrix expression for I. Okay, now I will just state what the matrix components of I are without going into much detail about why they're defined in that way. Okay. So the diagonal components of I are mx square, my square, mz square, and the off diagonal components are like this: mxy, mxz, my, myz, mz. So this is what the moment of inertia looks like in general. That if I have, so this is the moment of inertia for a point particle again. But now what I'm saying is that I have some rotational axis, which is some arbitrary rotational axis. Okay, and I have some point particle which is located at some arbitrary position. Okay, then the moment of inertia is given as of this point particle. So okay, no, I don't need the axis. Sorry, I'm sorry for that. Yeah. So the moment of inertia of this particle around the origin So this is located at some point x comma y comma z, and the moment of inertia of this point particle is given by this matrix. So if you have some solid object, okay, then what you will do is you will add up all this moment of inertia for all the points in that object. Okay, so you will get an integral. Instead of this, you will get something like this: the density times x square dx, and density times xy. So this will be integral of density times okay, I'm forgetting what the expression will be. Okay, anyways, you can look it up. Now we have the moment of inertia. If you have a symmetric object, for example, you have a sphere, something like this, and you want to talk about the moment of inertia of the sphere through around an axis which passes through the center of that sphere, right? Then in this case, all of these off diagonal terms, these are the off diagonal terms, they are going to be 0. Okay, and there is going to be only one term which is going to look like this, right? 2/5 mr square in this case. So you can calculate this term, moment of inertia. You can do this calculation by breaking up the disk, breaking up the sphere into small disks and cutting it into slices, and taking each slice and breaking each, and then cutting each slice into a ring, into a number of rings, calculating the moment of inertia for each ring, doing the integral, and when you do the integral for all of that, you get this factor of 2/5. Okay, so you have similar expressions for all kinds of objects. So if you have a cylinder like this, or you have a cylinder which is rotating around its long axis, the moment of inertia in this case is 1/2 mr square. So this is also the moment of inertia for a disk, because, well, these two are the same thing, right? And so on and so forth. You can always look up the moment of inertia if you don't remember what it is. Now, when we talk about this rotational motion, we have this concept of momentum, angular momentum. So we also have a concept of conservation of angular momentum. And this comes from the application of this Newton's law. That means if I have an object if I have some object which consists of two rotating bodies, and the first body has angular momentum L1, the other one has angular momentum L2, then these two are vectors. I can add them to obtain the total angular momentum. And if this is the external torque, if this is 0, then that tells me that L1 plus L2 is equal to a constant. So as a very simple example, you imagine that you have two disks. You have one disk and you have another disk. Okay, and the first disk has some moment of inertia I1, the second disk has some moment of inertia I2, and then you consider that you start out the system with disk 1 spinning at some speed ω1, all right, and the second disk is stationary at ω2 is equal to 0. Then the disks are brought together so that they meet in the middle. Okay. So they are brought together so that they meet. Then what will happen is they will both start rotating. right? They will both start rotating with the same angular velocity, let's say omega prime, which is not equal to 0. So the question is, how would you find this omega prime, right? So you would use conservation of angular momentum. Now, what is the initial angular momentum? It is I1 omega 1 plus I2 omega 2, but this is 0. What is the final angular momentum? It is just I1 plus I2 times omega prime. I can write this because, right, and right, I1 plus I2, because we're talking about the same axis of rotation and so on and so forth. So that tells me omega prime is going to be equal to I1 omega 1 divided by I1 by I2. Class a little bit more. Class. It's okay. Okay. So these sort of simple problems you should be able to do. All right. So I've talked about angular momentum today. I've talked about simple harmonic motion and wave. There's just a couple more things about wave motion that I should give you some background on. So wave motion is, there are some general expressions. So if you have a wave, I can write the expression for a wave as something like this: some a times sine kx minus omega t. This is the general expression for a wave which is moving in one dimension. Okay. Now, what are the value? What is this k and omega? Omega, as you know, is the angular speed. What is k? K is called the wave number. Okay. K is related to the wavelength by this expression 2 pi by lambda. Omega is related to the frequency by this expression 2 pi times the frequency. Now this wave has a velocity v, and the velocity, it can be written in terms of the frequency and the wavelength as lambda f, right? So this, what is this lambda f? This can also be written as omega by k. If you take this expression, divide by this expression, you get lambda f. So this is the general expression for a wave, right? Which is moving, which has a wavelength given by 2 pi by lambda, frequency given by 2 pi f, and a velocity which is given by omega by k. Okay. Then when we talk about waves, we can also talk about superposition. So that means I can take one wave, which is something like this, sine k1x minus omega 1t, and then I can add to that another wave which has a different wavelength and a different angular velocity. Okay. And I'll call this something, let's say g of xt. So here I'm just taking the superposition of two different wave motions. Now, when I take the superposition of these two motions, I can use, there are certain equations for adding this thing, sinusoidal functions. And for simplicity, I'll take this amplitude to be the same. Then this whole expression can be written as 2 times sine k1 plus k2 omega 1 plus omega 2 by 2t multiplied by cosine of k1 minus k2 x2 minus 2. Okay. this is just, I'm just using the expression for sine A, sine x plus sine y is equal to 2 times sine x plus y by 2 times cosine x minus y by 2. Right? Now, this kind of a wave exhibits what is called a beat phenomenon. Okay? So it is a combination of two different waves. One wave which has a high frequency, omega 1 plus omega 2, and another wave which has a low frequency, omega 1 minus omega 2. Right? So let us assume that omega 1 is equal to omega 2 plus some small delta omega, and k1 is equal to k2 plus some small delta k. Okay? So then this expression can be written as cosine of delta k x by 2 minus delta omega t by 2. Okay? So this is the slow part. This is the slow component, right? And this is the fast component. You can see that this is the fast component. It has a high frequency, right? Because frequency goes as 2 pi times omega. This guy has a frequency which is almost twice, right, for both omegas. It is short wavelength because the k is large. So it is the high frequency short wavelength component. This has a long wavelength and a low frequency. So it has a long wavelength, low frequency component. So if you look at the total wave, it will look something like this. This will be the small wavelength, high frequency, and then this part is the large wavelength, low frequency, right? And so this kind of a wave is called this kind of an object is called a wave packet. It's also called a wave packet. And we can assign a velocity to both of these components. We can assign a velocity to this component and a velocity to this component. Now the velocity of the slow component is what, looking at this expression, it is equal to delta omega by delta k. And this is also known as the group velocity, VG. Now, generally what will happen is omega will be written as a function of k. In that event, the group velocity will be written as the differential of omega with respect to k. Right? Delta omega by delta k, and the limit that delta k goes to 0 becomes the derivative. So this will be important when we talk about, well, it will be important in quantum mechanics and also in the electromagnetism section. Anyways, I'll stop here. Okay, I think this is enough for one class. We've talked about angular momentum, we've talked about waves, we've talked about harmonic motion and simple pendulum and so forth. Okay. And I think as far as classical mechanics is concerned, this much of a review is enough. I thought I was going to take more classes, but I think this is enough. So if you have any further questions about classical mechanics, you can always, well, you can read the textbook. Or you can ask me, or you can ask in the forum, in the Moodle forum, I'll set that up, okay? All right, so I'll stop here. Are there any questions now? Maybe I went a little bit fast, but again, I assume that all of you have encountered all of these concepts before. So this is not new to you. But if it was a little fast, remember I will be sharing these notes with you. So you will have that, but also you have the recorded lecture, which is available on YouTube for you to watch later. And then there will also be a homework set that I will provide later this week. Okay, questions?
Sir, you wrote a matrix form of what we say, I know, sir. In that thing, if the point is located at x-axis, all yz will be 0 na, sir. Then
Yeah.
moment of inertia should come mx square, but in that matrix it's coming 0 na, sir.
You will get mx square, no?
Like if I take this y and z coordinates to be 0, it's lying in x-axis. Only the first term of the matrix, that is 1 by 1, will be left, and everything becomes 0 na, sir.
Right.
So that time the matrix that comes out to be like 0.
No, the matrix is not 0, right? You have one non-zero component, no?
Like that means we should, like, it's not, we are not taking det of I.
No, we are not taking det. Nobody said we are taking det, no?
Okay, sorry, sir. Yes.
Right, we are taking the matrix product of I with omega.
Now understood, sir. Okay.
Okay, so if omega is along the z-axis, for instance, so the example you have, I can give you like what you asked, right? If the particle lies on the x-axis, and then what should be it's rotating this, what will be omega? Okay, never mind again. My brain is not working as well. You can probably figure it out faster than I will. But yeah, I mean, the moment of inertia tensor is a non-zero. And if it lies at a general arbitrary point, then all the components matter. But you can always take your axis and rotate them. If you rotate them to in such a way that your point lies on one of the axes, you will always get you will get a simplification. But if you have a complex body, then you have to take an integral over all the points. And when you take an integral over all the points, then you can't set some of the terms will remain non-zero.
Sir?
Yeah.
Sir, like the body that you made that is at an arbitrary point with coordinate x, y, z. Sir, for that, if we have to write the moment of inertia, so sir, can you write the expression? I mean, sir, this matrix, but by how we will get the result means the term that we have to put in calculation, how will we get it from the matrix? Or sir, this matrix is in vector form.
I'll give you some problems on Moodle, okay? In the homework assignment. I think that those problems will clarify some of your questions.
Okay, sir.
All right. So I'll stop the recording and